So how's everybody doing out there? Well, welcome to day 20 of Corona Online School. So today we're going to be continuing on with our study of hypothesis testing and actually getting in to try to do some hypothesis testing today for the first time instead of just setting them up and stuff like that. So it should be fun. Just a quick reminder, election day is coming up tomorrow, so there's no school at FCC. So, or if you're, depending on when you're listening to this, it's Tuesday, of course. And so make sure if you haven't voted already, get out there and vote. Every vote counts, so you should take advantage of your right to vote. So with that little plug in mind, let's jump in and actually talk about some hypothesis testing. So the first section we're going to talk about is just kind of summarizing the last two things that we want to think about when it comes to hypothesis testing. So there's the distributions and what kind of distributions we'll be using. And I mentioned this a little bit in section 1, but I'm going to go through it again. And then the last thing is just drawing conclusions and stuff. And so for us, for this section or this chapter, the three types of distributions that we're going to be using are going to be, claims about a mean when the population standard deviation is known. So hopefully we remember from our study of confidence intervals, this is when we would have used the z-interval as our way to solve that kind of problem. And that's the kind we're going to work on today. And then next class, we'll talk about the next two, which is when the population standard deviation is unknown. And that's when we're going to use our t-interval. And so in that case, we would get our t statistic, which is written down there, which looks just like a z statistic. And then finally, our last one is our probability or claim about a proportion. So in that case, that's one where we would use like the one prop z interval. Or some people just named p interval, which was good too. And so again, we've got, how to find our z-score. And so really it's just the same way we would find our z-score from above. So nothing super fancy or anything like that. All right. So when we're drawing a conclusion, we knew from before that there's basically two conclusions that we can have. So we can have our, reject H naught or our fail to reject H naught. The question is, how do we know when we can actually do one or the other? What allows us to say, this one's a reject, but this one's a fail to reject and stuff like that. So it's all going to come down to this thing called a p-value, which is just a probability, but it's going to allow us to actually use kind of what we learned with confidence intervals, but to put this p-value on it to make it so that we can kind of guarantee that we know that our claim is true and stuff like that. So just to briefly look, the p-value is just the evidence against a null hypothesis. So remember, the goal is we're trying to always disprove the null hypothesis if possible. We're always trying to claim the alternate hypothesis is true. And so the way this works is the smaller the p-value, the stronger the evidence that you should reject the null hypothesis. So in this case, if our p is low, we're going to reject H naught. If our p is not low, we will fail to reject H naught. So what do we mean by low, though? What's it mean to be low? Well, that's where our alpha level comes in. And if you remember, we had an alpha level for our confidence intervals, like a 92% confidence level or a 98% confidence level or a 95 or a 99. So that alpha level is the same alpha level we're going to be using when we're trying to actually solve these probability or these hypothesis testing problems. So one thing to notice is if there's no alpha level given, we always kind of assume that the alpha level is 0.05 or a 95%, like not quite confidence interval, but like that. So when we're looking at these, if our alpha was 0.05, if we can show that p is less than 0.05, then that means we can reject H naught, and our claim that H1 is assumption is that H1 is true is good. Or if we fail to reject H naught, then that means we're going to get a p-value that's greater than 0.5 or whatever the alpha level happens to be in this case. So with that in mind, let's actually dive in, try some examples so we can kind of see what's going on with these guys. All right. So let me switch to the next packet here. I'll just do it all as one video. So head on over to the 9.4 claim classwork packet, which is testing a claim about a mean sigma known. So again, this is kind of putting everything together, everything we've learned from confidence intervals, everything we've learned from hypothesis testing, and being able to make some kind of a claim about our information. So in this case, if we look, so we've got our example one is years of education. So a social scientist suspects that the mean number of years of education for adults in a certain large city is greater than 12 years. She surveys 100 adults and finds that the sample mean number of years is 12.98. Assume that the population standard deviation is 3 years. Test this claim. So in this case, if you'll notice, I've got this example laid out fairly well. And so this is the way you should kind of lay out all of your examples as well. So there should be 4 steps to solving any hypothesis test. So step 1 is going to be, of course, state the hypothesis. So that's going to be our null and alternate hypothesis with the appropriate population parameter and inequalities. Step 2 is actually finding the test statistic. So in this case, this is going to be our z-score for the sample, and see kind of how it relates to the population standard deviation in this case, or population mean and standard deviation in this case. So 3, now we're going to calculate the p-value that corresponds to this area that's shaded above and kind of see exactly where our data actually falls in this case. And then finally, we want to draw a conclusion about what we've actually done in this case. All right, so let's take a look here so we can see kind of what's going on. So let's kind of highlight some stuff first real quick. So a scientist suspects the mean number of years education for adults in a certain large city is greater than 12 years. So that sounds like it's going to be our alternate hypothesis. So she surveys 100 adults and finds that the sample mean number of years is 12.98. Assume the population standard deviation is 3 years, and then test the claim. So not that you have to do this, but I kind of like to write stuff down as possible. So in this case, so we know our n is going to be 100 in this case. The sample mean is going to be 12.98. Our population standard deviation is our sigma, which is 3. And then technically in this problem, there's no alpha given. So that means our alpha is going to be 0.05 in this case. All right. So that's all we need to, we really don't even need that for step 1. We're going to use it for step 2. Step 1 is just the hypothesis. And so again, if we go back up here to our greater than 12 years, that sounds like it's going to be our alternate hypothesis. So let's go ahead and do H1 is mu greater than 12. And then our H naught is going to be mu less than or equal to 12. So remember, these have to be opposites of each other. So if our alternate is greater than, then our null has to be less than or equal to in this case. And so down below, it's nice to kind of visualize what's going on when we're actually looking at these pictures and stuff like that, just to get an idea of, the information that we're going to have, like where's the data going to fall and stuff like that. So in this case, since this is an alpha level of 0.05, then what that means is this is actually going to be our alpha over here. So this is a little bit different than when we were doing the confidence intervals, because remember with the confidence intervals, we had to divide them in half and stuff like that. So in this case, that means there's 5% kind of in this blue area that we're trying to basically land in. We want to be somewhere less than 5%. So that means we want our p-value to be somewhere in this blue range. So basically, all this stuff over here, here's the 95% bad area where we're going to fail to reject H naught. So if you think about it this way, this is going to be our fail to reject H naught range. This is going to be our reject H naught range. So if you notice, there's a lot smaller area to try to reject H naught than there is to fail to reject H naught, which is probably a good thing. So that's a nice thing that this actually happens. And so again, you don't necessarily have to draw this all the time, but it does give you a nice indication of kind of what's going on. And so if we wanted to think about this real quick, like if you remember, like what would be the z value for this normal CDF in this case? So just to get a rough idea of where we would be at. So in this case, we would do our normal CDF on the calculator. Not normal CD, inverse norm, sorry. So we would do inverse norm. The area is 0.95. And then in this case, we were doing our mean was just 0 and 1, just to get an idea of what the z-score would be. So in this case, that 5% area is going to give us a z-score of 1.65, which I think we'd looked up before. And so this isn't the test statistic. This is just to kind of give us an idea of, well, I guess I could have used the mean in this case. Let me use the mean instead of the 1.64 since we've got the population mean instead. Sorry. Let's do inverse norm again. And so we're assuming the population standard deviation or population mean is 12 with a population standard deviation of 3. Oh, well, not that 3, like of the 3 over 100, sorry. All right, so this is telling us 12.49 approximately is where that kind of upper 5% is going to stand from our lower 5% in this case. So let me get rid of the 1.64. 12.49. So that's going to be kind of that z value that divides the lower 95% from the upper 5%, basically. So when we go and find our z-score for our sample, this will tell us kind of like where this actually stands. So if we look, we've already got our sample value. So notice our sample mean was 12.98, which is already to the right of this value. So it's already in this blue area. So without really doing anything at all, we can kind of say, hey, I know I'm going to be in this blue value already because 12.49 is the very edge of this blue value, and I'm at 12.98, which is somewhere up in this area. So this is kind of a good thing. This is telling us that our claim is going to be true, but we want to go through and formalize it the rest of the way. So let's find our z-score here, which is just going to be our x bar minus our mu, all divided by our sigma divided by square root of n. So this is going to be our 12.98 minus 12 all over 3 divided by square root of 100. And if I type this in the calculator, whoops, what am I doing? Oh, geez. 12.98 minus 12 is that, and then divided by 3 divided by square root of 100 gives us a z-score of 3.27 in this case. So our z-score is 3.27. And if you remember, I did accidentally pull up the z-score on this one, and we saw that the z-score was like 1.64 or something like that. So in this case, we can see that 3.27 is pretty unusual. We would have called that unusual before because it's kind of way outside of our realm that we're used to. So now we've kind of got two different indicators that we're in the blue area, which again is good, but we need to do this the right way. We need to get our probability so we can actually figure this out totally. So to figure out our p-value, so this is where we're going to use our normal CDF. And so the value we're checking is the 12.98. And so since it's greater than, we want to do 100,000 as our upper. And then our 12 is our population mean that we're testing against. And then our standard deviation is again going to be the 3 divided by the square root of 100. So remember, we have to use our central limit square root or theorem for the standard deviation. So now let's plug this in to the calculator. So normal CDF, 12.98, comma 100,000, comma 12, comma 3 divided by square root of 100. So don't forget the square root of 100 part, because if you don't, this will actually look perfectly normal, which it isn't. And then hit enter. Now be careful here, because I know some people on the quiz kind of, or on the exam or whatever, I guess messed up some stuff or quiz with these kinds of numbers. So remember, these are scientific notation is what this means. So let me write this down so we can kind of interpret it in a way that actually makes sense. So I'm going to write down 5.44 times 10 to the negative 4. So that's what that E means. So this is scientific notation, and it means, raise that to the negative 4 power. And so this is our p-value, what we've just found here. This is the probability of landing in that blue area above the 12.98, actually. So above the 12.98. So wherever it is, this is that value there. So now what we want to do is convert this into an actual percentage so we can compare it to 0.05. So remember, the way scientific notation works is if we've got a negative number, then that means we need to move our decimal that many places to the left. So in this case, let me put some zeros in front. And so I want to go 1, 2, 3, 4. So my actual number is 0.000544. And now the question is, we're comparing this to 0.05. And so which one's bigger? So 0.05 is definitely bigger. So the value that we were interested in is smaller. So in this case, our p-value is less than alpha, which is good. So since our p-value then we reject H naught. So there is sufficient evidence to support the claim. These answers are really long, as you can tell. So, and you should write these out. This should actually be written out as a paragraph every single time. So our p-value is less than alpha, then we reject H naught. So there is sufficient evidence to support the claim that, that the mean number of years is greater than 12? Yeah, so that the mean number of years of education for adults is greater than 12. Whew. So it's a lot of stuff to write out in this case. So, but that's the key. So this is what every single example will look like. Again, regardless of whether it's a sigma known, sigma unknown proportion. Like all these are going to be the exact same steps. So really the only thing that's going to change are just the population parameters and things like that. Like all this other stuff that we're going to do is going to be exactly the same. So notice all we've done is the same stuff we just did for confidence intervals, and just use that to be able to evaluate our probability, use our probability against our alpha value, and then kind of went from there. All right, is that okay with everybody? All right, good. So let's look at the next example here, and then I've got a bunch for you guys to try. So in this case, we're looking at test scores. So we've got a pre-test and a post-test. Post-test were given to workshop attendees. The pre-test score average was 24. And the researchers want to know whether the post-test score is significantly different from the pre-test score. So they sampled 50 tests and found that the sample mean was 24.8. Assume the population standard deviation is 1.2. And then use an alpha level or a significance level of 0.01 in this case. All right, so again, I like to write stuff down. So let's see. So we sampled 50 people, so our N was 50. We found our sample mean to be 24.8. We found our sigma was given to be 1.2, and in this case our alpha level is 0.01. Oh, and by the way, I forgot to mention, and you'll see it on this one. So notice on this one there's blue on both ends, and that's because of the type of problem it is. So the one that we did above, whenever you have either a less than or a greater than, this is always going to be called a one-tailed test. Because the success is only going to occur at one end or the other. So if it's a greater than, we're only going to get success if we're up at the upper end. If it's a less than, then it would be the opposite. We'd get success on the bottom end. So these are always called one-tailed tests, which I meant to mention and forgot. So the one that we have here is actually a two-tailed test. And the reason being is because since it's looking for significantly different, this is going to be one of those not equals equals situations. So that's going to be a two-tailed test, is whenever it's a not equals. All right. So let's state the hypothesis. Now I just kind of gave it away. So in this case, we're trying to test the claim that the post-test is significantly different from the pre-test. So they don't want to say it's bigger or smaller, they just want to say it's different. So in this case, to say it's different means we're going to get a mu not equal to 24, and that means our null hypothesis would actually equal 24 in this case. All right. So now with this one, we want to be a little careful because, again, since we're using this alpha as 0.01, then just like we did with confidence intervals, and this is a two-tailed test, and the probability is actually divided between the two of them. So if we take 0.01 and divide it by 2, then that's going to be kind of the percentage above and below in this case. So, oops. So let's see, so what do we get here? 0.01 divided by 2 is going to be our 0.005. So when we're looking at these probabilities, so if we were doing like we did last time, like we'd have an alpha level of 0.0005 here and an alpha of 0.005 there. And so the idea is, since they're not saying it has to be above or below, so we could fall in either of these two ranges. So we could be really, really low or really, really high. And in that case, that's still going to satisfy our claim, allow us to reject H naught and stuff like that. So this one's divided the way we do it. So when we do our confidence interval, we'll have to be a little careful of that too. So just, well, I guess we won't have to because we're not doing inverse norm or anything like that. We're just doing normal CDF. So we don't have to worry about that part of it or anything like that. All right, so let's look at our Z critical value here. So our Z again is going to be our X bar minus our mu divided by our sigma, all divided by the square root of n. So our X bar was the 24.8. Our regular mean is the 24. Our sigma is 1.2, and then divided by square root of 50. So again, let's throw this in the calculator just so we can see what kind of value we get. 24.8 minus 24 divided by 1.2 divided by square root of 50. So this gives us a z-score of 4.71. So this is actually even higher than the last one that we had. So this one should cry out for you that this doesn't look good at the moment. Because again, if we were to calculate what this z-score for this alpha level was, it's definitely not going to be anywhere near 4.71. So it sounds like we're pretty safe that this might be another reject H naught. But we really need to do the work just to make sure it really is. So now let's go down and look at our p-value for this guy. And so notice I did mention we have to multiply this answer by 2 because, again, it's split up between two different sections and stuff like that. So once we find our normal CDF, we're going to have to multiply this answer by 2 to make sure that we actually get the right p-value that we're looking for. So in this case, our normal CDF is going to be what is it, 24.8. And so again, I'm just testing the higher part of it, and then I'm going to get the bottom part for free, basically. So and you could do the bottom if you wanted. I just prefer to do the top, but. And then our mean was 24, and our standard deviation was again the 1.2 divided by square root of 50. So again, let's plug this into the calculator. 24.8 comma 100,000 comma 24 comma 1.2 divided by square root of 50. And so again, multiply this by 2 because this is just 1/2 of our probability. We've got the other half down below, so this is only testing the upper half, so we need to include the lower half as well. But since it's symmetric, all we have to do is multiply it by 2 to do that. So in this case, we've got 2.43 times 10 to the negative 6. So let's write that down. And so again, converting this into a number where we can actually compare it. So we've got to put a bunch of zeros in front and then move it 6 places. So 1, 2, 3, 4, 5, 6. So our p-value is going to be 1, 2, 3, 4, 1, 2, 3, 4, 5. 243, which is clearly a lot less than 0.01. I mean, it's a lot less than a lot of other things in this case. So this is a clear, definite reject H naught. So again, since our p-value is less than alpha, we reject H naught. So, how did I word it last time? I want to make sure. So there is sufficient evidence. I want to make sure I get the wording right. So there is sufficient to support the claim that the post-test score is significantly different than the pre-test score. And that's it to it. So it's a little messy, it's a little complicated. I mean, but once you get the hang of it and do a bunch of practice ones, which I've got a bunch of them on here to do. So again, remember, these are all just using like the Z intervals and stuff like that. So again, it's related to the confidence intervals we've been working on. Again, you can kind of use these values as sort of a judge to figure out whether we're on the right track or not. Again, calculate our p-value, compare it to the alpha. If it's a two-tailed test, you just compare it right away. If it's a one-tailed test, you just compare it right away. If it's a two-tailed test, remember we have to multiply it by 2 and then compare it, which in this case didn't matter. I mean, even the one-tailed was good enough, but so we need to make sure we do that. Otherwise, try these on your own. Let me know if you get stuck or have any questions. I'll be around the computer all day, so good luck and have fun.